The amazing colossal integer sequence and the golden ratio. Amazing? Yes. And colossal? Yes. Why? Because the integer sequence is infinite in both its length and its breadth, and its simple yet profound mathematical links. What links? It is linked to infinitely many linear and quadratic equations, the difference of squares, the golden ratio set of identities, and the Pythagoras theorem. Is that enough? I revealed the integer sequence to myself, starting with the golden ratio, and then finding the set of allied identities. I shall start with the integers and end with the golden ratio. Create an infinite column 1 of the integers starting at 1. Generate column 2 by adding the integer in column 1 to the one that precedes it. Generate column 3 by adding 2 less than the difference between column 1 and 2 to column 2. Generate column 4 by adding 2 less than the difference between column 2 and 3 to column 3. Generate column 5 by adding 2 less than the difference between column 3 and 4 to column 4. Generate column 6 by adding 2 less than the difference between column 4 and 5 to column 5. We can continue generating columns of integers in exactly the same manner ad infinitum. The red numbers 1, 5, 11, 19, 29, 41, 55 form a quadratic sequence whose equation is y equals x squared plus x minus 1. The blue numbers 3, 8, 15, 24, 35, 48, 63 form a quadratic sequence whose equation is y equals x squared plus 2x. The black numbers, which are the sum of the red and the blue numbers 1, 8, 19, 34, 53, 76 form a quadratic sequence whose equation is y equals 2x squared plus x minus 2. The important sequence of numbers is 5, 12, 21, 32, 45, 60 and 77, which is the fundamental quadratic sequence whose equation is y equals x squared plus 4x. It is obvious that the arrays of integers produced splits into two more integer arrays. The first one is the odd integer array. The numbers lying on the blue diagonals fit easily defined linear equations, and those on the red diagonal fit predictable quadratic equations. And the second array of integers comprises both odd and even numbers. Again, the numbers lying on the blue diagonals fit easily defined linear equations, and those on the red diagonal fit quadratic equations. Behold the set of golden ratio identities starting with the golden ratio. The two roots are produced by the method of splitting the square. We take the square root of 5, 12, 21, 32, 45, 60, which again is the fundamental quadratic y equals x squared plus 4x, so the golden ratio identities are infinite. The product of the roots of the golden ratio identities produces the first column of integers in our table. The fundamental quadratic sequence has the successive differences of odd numbers starting at 7, 9, 11, 13, 15 and so on and so forth. They are also formed as the difference of two squares and the product of two integer sequences with a difference of 4 and linked to pronic numbers. The difference between the two numbers that are summed in the fourth column of the preceding table are all perfect squares. We then have the set of golden ratio quadratic equations. All rows and columns of integers are formed by applying the binomial partition of the integer to the integer part of the roots, as the following demonstrates for the integer equal to 7. We can then see that this generates the additional numbers across the row. QED. Take a square and partition it into two, so that we can then say that each side consists of 2 units, so that the square has an area of 4 square units. We then divide the two rectangles produced diagonally to give 4 equal triangles of sides about the right angle of 1 and 2 units and area equal to 1. We can rearrange the 4 similar triangles as 2 rectangles as right angles to one another as shown. Then triangles A and C can be rotated and combined to form the final figure of 4 triangles plus a central square contained within a larger square. It is self-evident that the inner square has unit side and area combined with 4 triangles of unit area, means that the new larger outer square has an area of 5 square units. Labelling the larger side about the right angle A, the small side B, and the hypotenuse, which is now the side of the square containing the whole figure, as C, so that the inner square has side A minus B. We can therefore deduce that the whole figure is algebraically defined as C squared equals 4AB divided by 2 plus A minus B all squared, which is equal to 2AB plus A squared minus 2AB plus B squared. So the 2AB's cancel to give us C squared equals A squared plus B squared, QED. Numerically, C squared equals 2 squared plus 1 squared equals 4 plus 1 equals 5 equals the square root of 5 all squared, and C therefore equals root 5. Rotating the centre square until its sides are parallel with those of the outer square, i.e. they have a common centre and coincident diagonals, we obtain the algebraic identity A plus B all squared minus A minus B all squared equals 4AB, the quarter squares rule, which is actually not a rule but a theorem due to Euclid and proved in his Elements, Book 2, Proposition 8. In his Elements, Book 6, Definition 4, Euclid stated, a straight line is said to be divided in extreme and mean ratio when the whole is to the greater segment as the greater segment is to the less, from which we can calculate that A is the golden ratio and B the conjugate. They can also be calculated as follows for a square equals 5. From the diagram, A plus B equals A minus B plus 2B. Therefore B equals A plus B minus A minus B all divided by 2. A plus B equals root 5 and A minus B equals 1. Therefore B equals root 5 minus 1 over 2. This gives the two roots for the golden ratio QED. Based on infinite fraction representation of the integers, does 1 equal 0.9999 expanded to infinity, as rigorously argued by many mathematicians based on Leonhard Euler's method given in his elementary algebra? Well, the golden ratio identities demonstrate that the equality is not valid, because the old decimal root gets closer and closer to 1 as the integers get larger, but can never ever attain 1 since the integers are infinite in extent. If the mathematician's assertions are correct, then the integers are not infinite, a contradiction. Also, 1. Integer plus 0.9999 to infinity times 0.999 to infinity equals integer, whilst 2. Integer plus 1 times 1 equals integer plus 1, which according to the above equality should be equal, a contradiction, QEF. This demonstrates the dangers of a cocksure mathematician writing a mathematics book called How Never to Be Wrong and including 1 equals 0.999 expanded to infinity in it. No matter how big the expansion, it is still after all an approximation, not an equality.